All right, in this unit, we're going to switch gears. We've looked at differentiation so far in multivariables, but now we're going to look at multivariable integration. So let's, to introduce this idea, uh, just as we did in single variable calculus, when we started to introduce integration for the first time, to introduce multivariable integration, what we're going to think about are Riemann sums. So we're going to first look at how we can approximate integration, but then we'll look at some more formal integration techniques. Well, this three-dimensional map, we can start using this three-dimensional map as a way to think about Riemann sum approximation. So in this, we're looking at the population density of foxes in southwestern England. And the three variables here are the kilometers measured east-west, the kilometers measured north-south, and then we've got our contour map, which is telling us the density of foxes. So for example, everything on that blue line just drawn has a density of 2. Everything on this red line would have a density of 1. So what if we wanted to approximate the number of foxes? How would we do that? Well, we'll come back to that in a second, but let's do a little bit of review of single variable integration first. So in single variable integration, we used Riemann sums as an approximation. So let's just imagine that we have some function f of x from a to b. And I wanted to approximate the area underneath that curve. Well, we know now that the math behind that is the integral from a to b of f of x dx. And that gives us the area under the curve. But let's say that we don't have an actual function and we're just trying to approximate that area. The method that we use is by using Riemann sum. So let's use a Riemann sum with n equals 4, and let's do a left bound. So the process was to take our interval from a to b, and we're going to break it up into 4 parts. And since we're using a left bound, on my first little range, I'm going to use the left value, and I'm going to create a rectangle. And I can find the area of that rectangle. The area of that rectangle would be f of a, that's this value here, that's the height of it, times b minus a over 4. Because b minus a over 4, that's the length. And then I would get the next value. So the next value is right here using the left, creating a rectangle. And so this value here, that's a plus b minus a over 4. So that y value is f of a plus b minus a over 4. And then I'm going to multiply that by b minus a over 4, the width. And I could continue that process, that same process, to find the remaining 2 rectangles. So we'd add up these areas. And notice, of course, that it's not a perfect science. We have error in this, and we can see that error. We're missing area right there that isn't being added. So it's not a perfect system, but it's a way for us to approximate area. So similarly, we can think about this system, and just like we had 4 rectangles there, we can break up all these boxes. And each one of those boxes has an area. So the area of each box, well, it's a width of 30 and a height of 25. So that's the area of each box. And then what we're going to do is we're choosing here, and it doesn't always have to be the northeast or the upper right, but we're going to use the northeast corner as a way to approximate our population. So if we do that, uh, you know, here's my approximation for the first box, and that's 0. And all of these 0, 0, 0, 0, 0, all of these densities here are 0. And then, so let's go into where the fox actually live. So in this box, my upper right-hand corner, my northeast corner, that was a value of 1. And in this box here, that's a value that's just a little bit bigger than 1. It's in between 1 and 0.5, so let's say like 1.2. We'll do a couple more boxes. And so in this box here, that value here is 1.5. So I'm writing the densities in each of those boxes. And what I'm doing is I'm using the northeast corner to approximate the density over the entire box. Now, this is an approximation because as you notice, density is changing. That's 1.5 along this line, but here it's 1 and here it's 0.5. So clearly, it's not 1.5 throughout. Do just a couple more. So then we've got this box here, and it's roughly 2. So we'll put 2, and we've got this box here in the bottom, and that's just a little bit more than 0.5. So of those boxes that I've drawn, so I'm not going to go through and do each one of these, but of these boxes that we've shown, so of the shaded area, we can use those density approximations to predict the total number of foxes in the area. So that our prediction would be 750, which is the area of each box, times, well, a bunch of zeros, and then 1 plus 1.2 plus 1.5 plus 2 plus 0.5. And just to be totally, to make it a little bit clear, this value, the 750 times 1, is saying that we had an area of 750 and a density of 1. So 750 times that density of 1 would give me the number of foxes. So the idea is we'll be given some function, m, and our function of m is going to be changing, and we're going to multiply our m. So to parallel this with the fox, this was like our density. And so then we're going to multiply that density by our area, the change in x over change in y. So we've got, just to write that a little clearer, the sum of, so from I to j, of m I j, and this is saying the density at different values, multiplied by delta x, delta y. So clearly, if we want to make this approximation as accurate as possible, what we're going to want to do is take the limit as delta x and delta y approach 0. So in other words, instead of looking at a big box, let's look at a smaller box, and let's actually look at a much smaller box than that. So the smaller that we can make delta x and delta y, the more accurate my approximation would be. And just to go back to the fox population, if we think about that, if we draw a little small box, let's say like a little small box right there, you're more likely to capture the accurate density versus a box such as this one, which has multiple densities in it. So we're missing information when the boxes are too big. Okay, so using that idea, extending this idea a little bit further, the single variable integration resulted in area. That was the geometric interpretation of single variable integration. Likewise, when we integrate a two variables, so we have some function that depends on x and y, and we're going to integrate it with respect to x and with respect to y. This is going to result in, well, as we can see from these pictures here, that's going to result in volume. So in other words, we're going to take some area, that dx dy, and we're going to add volume to it. So imagine, this becoming three-dimensional stuff coming out of the page. Okay, so let's look at examples where we're not talking about Fox anymore, but we're just talking about a three-dimensional system in terms of x, y, and z. So let's think about x, y, and z as just being length. There's some value of length, and we have some value f, which is positive. The idea of f being positive is just saying that we're not dipping below the xy plane here. So then the volume under our graph of f above some region R, so above the region R, is the integral over the region R of my function dA. And what we're going to look at later on is that we're going to be writing this as a double integral because we're going to integrate with respect to x and then integrate with respect to y, but that's coming up, so let's just hold off on that. So how do we go about and approximate this volume? Well, let's consider some function here. We've got z equals e to the negative x squared plus y squared. And we want to look at the rectangle between 0 and 1 and x and 0, 1, and y. So we've got 0 to 1 and 1. So here's my x value and here's my y value. And we want to use a Riemann sum to make an upper and lower estimate of the volume of the region above R and under the graph of this function. So in other words, here's my graph of z. What I want to do is find out, what is this volume, all of that volume underneath the curve down to that region on that one-to-one box. Okay, well, how do we do this? Let's first look at an upper estimate. Well, in an upper estimate, we need to think about what's going to make my estimate bigger or smaller. So in other words, if I put x and y values into this equation, the bigger the x and the bigger the y value, the smaller my z value. I could rewrite this function as z equals e to the x squared plus y squared. So the bigger x and y are, the bigger x and y are, the bigger this is going to be. And the bigger my denominator is, the smaller z is going to be. So as x, y increase, z decreases. So if I were to think about doing an estimation, doing an upper estimation of this volume using a 9 boxes as such, we would split up my values in 2/3. And if I wanted to find the upper approximation of my z value on that region, if I wanted to use the upper value, if I want z to be as big as possible, I'm going to make x and y small. So for this given value, I'm going to choose x equals 0, y equals 0. So my z value is going to be e to the negative 0, which is just 1. So I get z equals 1. And if I look at the next box, like this box here, if I want to make z as big as possible, what I'm going to choose are the smallest x values and the smallest y values. So that's going to occur right here. That's where x is 0 and y is 1/3. There's no smaller combination on that box. So then my z value is going to be 1 over e to the 0 plus 1/3 squared. So that's 1 over e to the 1/9. Let's make that a little bit bigger. And maybe I'll just leave it as a negative. That's e to the negative 1/9. Okay, if I want to find this box using an upper estimate, again, I'm going to use the smallest x and y combination. So that's going to happen when x equals 0 and y equals 2/3. And so my z value is going to be e to the negative 0 plus 2/3 squared, which is e to the negative 4/9. Now, I think you understand the problem. Let's do one more of these, and then we'll show how we use that to approximate the volume. So just to do one more, let's just choose this value right in here. So I want to approximate, see what z as big as it's possible as it could possibly be, and that's going to be at that point there when x equals 1/3 and y equals 2/3. And so my z value is going to be e to the minus 1/3 squared. So minus 1/9 plus 4/9, which is e to the minus 5/9. So if we wanted to then use that work that we've just done just to approximate the volume on this little region, and I don't want to go through and find the rest of the boxes. So if I wanted to find the volume of underneath the curve z equals this on that little weird uh, of sectional couch shape, what it would be is the area of each of those boxes, and the area of each of those boxes are 1/3 times 1/3 multiplied by each of the z values inside. So my first box had z equals 1 plus z equals e to the negative 1/9 plus e to the negative 4/9 plus e to the negative 5/9 plus, and then dot 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 dot. But this section in here is the area, sorry, is the volume under the curve of this sectional couch. And so the idea being you create these little small areas and you find the maximum z value in that area. And then you do area, then you do area times the z value and add up all of those z values, and that will approximate the volume. So just kind of seeing this in terms of a table, let's say we had 16 divisions. The more divisions, the better. And once again, we're looking at the same function. And for this function, it has, for all of the, all the y values up here and the x values here. So if I wanted to find, for example, let's get this table down. So again, this is the base of the region. It's the base of this region right here. It's this section in there. And what's going to go into these boxes are the z values. Some z value, some z value. So if I wanted to find the z value of this section right there, that's when x is between 1.5 and 3/4. And when my y value is also between 1.5 and 3/4. So we're looking at this region in here. So if I wanted to find a max approximation, what I would do is say, okay, well, which one of those z values in this region is the biggest? And clearly the biggest value is 0.6065. So the little bit of volume, so the change in volume from that one box is going to be 1/4 squared, and that's the area, times the z value, 0.6065. is x5. So again, that's my change in x times my change in y times my function, and we'll call that function m. So just to make sure that you get this, why don't you pause the video in a second and see if you can approximate what the volume would be from this little section. Pause the video and see what you can do. Okay, well that's looking from x and y going from 0 to 0.25. So we're looking at these values right in there. And what we're doing is we're saying, okay, in that region, in this region, which is this region, what's the biggest z value? The biggest z value is 1. So the change in volume, or the volume added from that little square, would be the change in x times the change in y, or 1/4 squared, times my z value, 1. And again, that's my change in x times my change in y times m. And then the idea is we're going to add up, we're going to sum all of these m values. So the incrementing by ij, meaning incrementing by i's and j's to figure out what the m value should be, times my change in x times change in y. And uh, the last idea is just an extension of something that we looked at in single variable calculus. So as a reminder of average value of a function. So if I have some function f of x from a to b, and I wanted to find the average value of the function from a to b, if I integrated f of x dx from a to b, what I'm going to find is the area. And then if I divided by b minus a, what I'm doing is I'm taking my area and then I'm dividing by the length. So what I do is I take my area, which is height times length, and divide by length. So units wise, what I'm left off with is the average height. And graphically, what this represents is the average height of that function on the interval. So the similar extension is in 3 dimensions. If we integrate a function with respect to dA, what that gives me, this gives me the volume of a surface. So for example, right here, on this graph here, what that's giving me is the total volume over that whole entire um, region. So how much volume does that function contain? But then if I take my volume and I divide it by the base area, so if I divide it by the area, this area down here, all that area, what I'm left with, if I take volume by area, what I'm left with is just the height, or the average z value. And what that's represented on a graph is a plane. Let's see if I can get this plane. It's this plane here that's drawn. It's that plane which is the average z value. So this is going to return a plane that's parallel to the xy plane and perpendicular to the z plane, or to the z axis. So this says, on the area, over that area R, on the region R, this circled value finds the average z value, written twice. So that's an introduction to integration in in many variable with many variables. All right, thank you.